Hello dear students, welcome back to our HMT class. Today we will derive the effectiveness NTU relationship for counterflow heat exchanger. In the previous class we derived the effectiveness NTU relationship for parallel flow heat exchanger. Okay, before going to the derivation of counterflow relationship, I would like to add one more point to the previous derivation. We started the derivation of effectiveness NTU relationship for a parallel flow heat exchanger by first assuming that hot fluid is equal to minimum fluid, and we obtained the relationship effectiveness is equal to 1 minus e to the power of minus NTU into 1 plus C min by C max divided by 1 plus C min by C max. Remember, CR stands for the ratio of specific heats, like this. Now, after obtaining this relation, just add a statement that the same relationship will be obtained if it's assumed that C cold is equal to C min and C hot is equal to C max. So same relationship can be obtained. So I add this point that if it's asked for the examination, do this procedure by first assuming that CH is equal to C min and obtain this relation, and add the statement. The same relation will be obtained if it's assumed that C is equal to C min. Now we will derive the relationship for effectiveness NTU for a counterflow heat exchanger also. Before going to the derivation, let's first see these relations. We have heat transfer or heat exchange is equal to C min into THI minus THO, which is also equal to C max into TCO minus TCI. Why? Because here we assume that hot fluid is a minimum fluid. So C min stands for C hot, C max stands for C cold. So heat transfer can be expressed by either of these relationships. From these two relations, we can write C min by C max. The ratio of specific heats can be written as TCO minus TCI divided by THI minus THO. Also, Q max is equal to minimum C min into maximum temperature difference. So in this case, C min into THI minus TCI. Thus, now we can write TCO minus TCI in terms of THI minus TCI. So TCO minus TCI can be written as C min by C max into THI minus THO. C min by C max into THI minus THO. And this THI minus THO in turn be written in terms of the effectiveness and maximum temperature difference. So THI minus THO will be written as epsilon into THI minus TCI. Therefore, TCO minus TCI can be written as C min by C max into epsilon into THI minus TCI. This relationship will be useful for simplifying the forthcoming equations. Now, let's see another point, that logarithm of THO minus TCI divided by THI minus TCO is equal to minus U into 1 by CH minus 1 by CC into area. This relationship was obtained during the derivation of LMTD for counterflow heat exchanger. Okay, let's also go back to a previous slide. In this one, we had seen a relation like this. Logarithm of THO minus TCI divided by THI minus TCO is equal to minus U into 1 by CH minus 1 by CC area. This relationship was obtained as an interim result during the derivation of LMTD for counterflow. Either you have to learn this relationship by heart, or you just obtain this relationship by deriving this. Now we'll go back to or derivation THO minus TCI divided by, so this was a relation, THO minus TCI divided by THI minus TCO is equal to okay, THO minus TCI, THI minus TCO is equal to minus UA into 1 by CH minus 1 by CC, where CH and CC are heat capacity rates. Therefore, this can be written as logarithm of THO minus TCI divided by THI minus TCO is equal to minus UA into this, which is equal to minus UA into minus UA by C min. See, this is a relation which I've already seen. So minus UA by CH is equal to C min. So the C min is taken outside. So minus UA by C min. So this will become 1 by C min. Sorry, 1 minus. Since this has been taken outside, this will become 1 minus CH by CC or C min by C max. So this is actually NTU. Minus UA by C min is number of transfer units or NTU. So now we will get log THO minus TCI divided by THI minus TCO is equal to minus NTU into 1 minus C min by C max. Or if we remove the logarithm here, right side will become exponent. So THO minus TCI divided by THI minus TCO is equal to e to the power of minus UA by C min into 1 minus C min by C max. Now, see the next step. THO minus the left side of that equation is THO minus TCI divided by THI minus TCO. We will try to make this ratio of temperatures to a comfortable form, like either this should be THO minus THI or TCO minus TCI or THO minus THI, like that. So these relationships, we will make some manipulations on this term numerator THO minus THI. So if we have a THI here, we can make some meaningful temperature differences. So THO minus, I'll subtract and add THI here in this numerator. So this will become THO minus THI plus THI. So numerator is the same. If I add and subtract THI terms, no change is there for the numerator. And for the denominator also, we will make a change. THI minus TCO. So what we do, we want to get something like if you subtract and add TCI here, again the denominator will also become some meaningful combination of temperature differences. So THI minus TCO minus TCI plus TCI. We subtract and add TCI terms here in the denominator. So let's see what the numerator and denominator terms can be there. So THO minus THI, we will make it THO we will take this term THI minus TCI, and we have THO minus THI, we will make it minus of THI minus THO, THI minus TCI minus of THI minus THO, and the denominator will see THI minus TCI are taken together, THI minus TCI. This is the maximum possible temperature difference in the heat exchanger, and the remaining terms are taken as minus TCO plus TCI. This is written as minus of TCO minus TCI, minus of TCO minus TCI. Now we have THI minus TCI minus THI minus THO divided by THI minus TCI minus TCO minus TCI. Now THI minus TCI is kept as such. Now what is THI minus THO? Let's see the other one, a previous slide. THI minus THO is written as THI minus THO. Okay, I'll go to the presentation mode here. THI minus THO is equal to epsilon into THI minus TCI. See, THI minus THO is equal to epsilon into THI minus TCI, and THI minus TCI is written as such. TCO minus TCI, if you remember, TCO minus TCI is equal to Cmin by Cmax epsilon into THI minus TCI. The same relationship we used here. This is why we wrote the previous relationship in the first slide. So Cmin by Cmax into epsilon into THI minus TCI. Now the beauty of this type of manipulation is that we have all the terms written in terms of THI minus TCI. THI minus TCI, denominator also THI minus TCI. So from all the four terms, we can take THI minus TCI outside and cancel. So after cancelling THI minus TCI from all the four terms, we will get 1 minus epsilon divided by 1 minus Cmin by Cmax epsilon. 1 minus epsilon divided by 1 minus Cmin by Cmax epsilon. So the left side of that equation is written as 1 minus epsilon divided by. See, now this was actually a temperature difference ratio, which is in turn be written as a function of epsilon and ratio specific heat. It's so simple. And what was the right side? The right side was e to the power of minus UA by Cmin into 1 minus Cmin by Cmax. UA by Cmin, as all of us know, it is called the number of transfer units for NTU. So e to the power of minus UA by Cmin into 1 minus e to the power of minus UA by Cmin into 1 minus Cmin by Cmax. Now from these relationships, we can separate out epsilon. So 1 minus epsilon is equal to 1 minus Cmin by Cmax epsilon into this, cross multiplying this. 1 minus epsilon is equal to, so now there are like 1 into e to the power of this minus Cmin by Cmax epsilon into e to the power of this. That's what it's written here. Cmin by 1 into e to the power of minus UA by Cmin into 1 minus Cmin by Cmax minus Cmin by Cmax epsilon into the same thing here. So now there is one term on the left side and one term on the right side that has epsilon in it. So writing the terms containing epsilon together, so we'll take this minus epsilon to the right side and at the same time this term onto the left side. So epsilon into 1 minus Cmin by Cmax, epsilon into 1 minus Cmin by Cmax e to the power of minus UA by Cmin is equal to this term. So finally we will get epsilon is equal to 1 minus e to the power of minus UA by Cmin into 1 minus Cmin by Cmax divided by 1 minus Cmin by Cmax epsilon into 1 minus Cmin by Cmax x e to the power of minus UA by Cmin. From this relation you can simply very easily get this relation. Now the beauty of this is epsilon is explicitly written in terms of NTU and ratio specific heat. This does not have a term of temperature in it. So even though you don't know the all the temperatures, we can find epsilon. Once we get the value of epsilon in terms of NTU and other parameters without knowing the temperatures, now epsilon multiplied by Qmax will give us the actual heat transfer. This is the beauty of this type of relation. Now we had seen the derivation of counterflow heat exchanger for parallel counterflow and parallel flow heat exchanger. Effectiveness NTU relationship for counterflow and parallel flow heat exchanger. Like this. This is for parallel flow heat exchanger and this is for counterflow heat exchanger. There is an error in the second equation. It should be negative. And for parallel flow this was positive and counterflow this is negative. So now if it's an evaporator and condenser etc. For evaporator, condenser etc. We know that if it's a condenser for evaporator, Cmin by Cmax will be 0 because if there is an evaporator or condenser, one of the fluid will be changing its phase from liquid to vapor or vapor to liquid, like that. So in those cases Cmin by Cmax will be 0. If you in this relation, if we substitute Cmin by Cmax equal to 0, this will be 1 plus e to the power of minus NTU divided by 1. So 1 plus e to the power of minus NTU. Similarly, for counterflow, this will become 1 minus e to the power of minus NTU. This term will become 0 divided by the entire denominator will become 1. So for parallel flow 1 plus e to the power of minus NTU, and for counterflow 1 minus e to the power of minus NTU. Now for other configurations, so parallel flow, a double pipe heat exchanger, parallel flow and counterflow, we have these relations. Now one more thing I would like to point out is that from this relationship we can also obtain a relation for NTU in terms of epsilon. Epsilon can be written in terms of NTU or NTU can be written in terms of epsilon. That is also there. Such a relationship will be there in the data book depending on the question in the problem. Either we will have to find out the effectiveness knowing the value of NTU, or we will have to obtain the value of MTU knowing the value of effectiveness. So for parallel flow and counterflow, these are the relations. This will be there in the data book. And for other parameters, other configurations, for shell and tube heat exchanger, this will be the relationship. And for cross flow heat exchanger, we have these relationships. So by making use of these relationships, we can obtain the value of epsilon for any configuration. These equations or the corresponding charts will be available in the heat and mass transfer data book. You can make use of that. So with that we conclude the derivation of counterflow heat exchanger.